So in this section, we look at a class of reactions known as paracyclic reactions. Now, this will be a very, very brief look at these types of reactions. A thorough look would take much, much longer than we have in this course. So we'll mainly focus on the Diels-Alder, which is the best known and possibly the most important of this class of reactions. But paracyclic reactions are reactions that typically have two properties. They occur through a cyclic transition state, and are concerted, which basically means that they happen in a single step. So paracyclic reactions are broken down into three primary categories. There are electrocyclic reactions. This typically involves something like cyclization of a polyene and might look something like this. So you can see here we have a triene here, conjugated triene, and our pi electrons shift around in order to form a ring. We have sigmatropic rearrangements. These also involve cyclic transition states, but they don't involve formation of a ring. So it might have something like this. Again, similar flow of pi electrons, but just we're not forming a ring in this case. And one of the more important examples of this reaction is a reaction known as the Claisen rearrangement. Now, in your textbook, this reaction may get covered in the reactions of ethers. I've chosen to cover it here in this section because mechanistically this is where it belongs. But it's a reaction specifically for a class of molecules known as aryl-allyl ethers. And so in a Claisen rearrangement, we need an oxygen attached to our aromatic ring, and then an allyl group directly attached to that oxygen. And you need high temperature, 250 degrees Celsius, for this reaction to go. And that's because the first step of this reaction is actually very unfavorable. In the first step of this reaction, we're going to see that shift of pi electrons to get our cyclic transition state. But notice, we start with an aromatic ring in this step. At the end of this step, our ring is no longer aromatic. And as we know, we get huge stabilization from aromaticity. And so a reaction that breaks aromaticity is usually not favorable. But it's actually relatively easy to get it back. You notice we have a carbonyl, and we've talked plenty in the carbonyl chapters about tautomerization reactions, or the conversion between an alcohol or an enol and its carbonyl form. And this is an example of a tautomerization where the enol is favored, because if it goes back to the enol, it regains aromaticity. All right, but for the rest of this section, we're going to be focusing on cycloadditions, which are our third class of reactions. Here, two unsaturated molecules combine to form a ring. One such example is this reaction here. This is an example of the Diels-Alder, which we'll talk more about in a little while. But in actuality, we've already seen a cycloaddition reaction. We covered it in the aldehydes and ketones chapter, but if you recall the Wittig reaction, in the Wittig reaction, the first step of that process, the one that made the oxophosphate intermediate, was an example of what we call a 2+2 cycloaddition. And those numbers that we mentioned there are the number of pi electrons from each compound. So we're going to talk more about this first example, the Diels-Alder, in a little bit. But before we can do that, we really want to talk about why conjugated compounds are different from non-conjugated compounds. And one of the first places we notice that is if we look at the bond lengths. And so if we look at a single bond that's next to a double bond, and then a single bond that's between two conjugated double bonds, we find that when it's conjugated, that single bond is a little bit shorter, which means it's a slightly stronger bond than we would normally find for an alkane. We can also see that conjugation gives us stability from looking at heats of hydrogenation. If you recall back to the aromatic chapter, we used these to measure the amount of energy, the amount of stability we got from an aromatic ring. Well, we can do the same thing for conjugation. So the heat of hydrogenation for just a single alkene like this, negative 30.1 kcals per mole. If we have two alkenes in the same compound, but notice we have an sp3 carbon between them, so they're not conjugated, we get what we would expect, which is almost exactly double the value of one bond, one double bond. But when they're conjugated, it's a bit lower. In fact, about 4 kcals per mole lower than when we just have two alkenes. And so again, that shows us that this idea of conjugation is a stabilizing effect. All right, so why is that? Well, there's a lot of reasons that we can go into, and we're just going to get into a couple of those reasons here. So we're going to look at the central bond here in each of these three compounds. In the first case, that central bond is between two sp3 carbons. In the next case, it's between an sp3 and an sp2 carbon. And when it's conjugated, that central bond is between two sp2 carbons. Well, we know that sp2 orbitals contain more s character than sp3, and so that makes them stronger bonds. But it turns out that there's also a more complicated situation. If you recall back to general chemistry, when you learned about pi bond formation, at some point you saw a diagram that looked like this. And when those two p orbitals combine to form the pi bond, we get a bonding orbital which is lower in energy, and then we get an anti-bonding orbital which is higher in energy. So how does that affect us here? Well, when we have a conjugated system, such as in butadiene, that means we have 4 consecutive carbons that are all sp2. And when we made the alkenes, or any pi bond, those extra p orbitals that were not involved in the hybridization were what combined to form the pi bond. Well, if we've got 4 sp2 carbons in a row, then all 4 of those p orbitals can combine to make an extended pi system. And so those are going to combine to form 4 new molecular orbitals, which we label, top 2 are Psi3 and Psi4 star. Those are anti-bonding. And then we have the 2 lower energy bonding orbitals. Our second one is exactly what we would expect for 2 alkenes. Our same signs, we have a node here in the middle between C2 and C3. And so this situation looks exactly like 2 pi bonds. One on the first 2 carbons, one on the second 2 carbons. And then we also have these higher energy ones, which don't really matter as much in this situation because they're going to be empty. But the Psi3 has 2 nodes, and Psi4 has 3 nodes. But Psi1 shows us the answer to our question as to why conjugation is stabilizing. Psi1 here, we can see, has no nodes. And so the 2 electrons that are in Psi1 are shared by all 4 atoms, or we can say they're delocalized over all 4 atoms. And this point in the course, how many times have we said that anytime we can delocalize electrons, that's a stabilizing effect? And we can have longer conjugated systems. We could have 3 conjugated or 4 conjugated or more. And so the more conjugation we have, this effect increases and the molecule becomes more stable. Now, in terms of reactivity, this actually leads us to some interesting consequences. The very first reaction we learned in this course was the addition of HBr to an alkene. We know that gives us this product. But what if we tried this same reaction with a conjugated diene? Well, here it depends on our reaction conditions, specifically the temperature. If we run this reaction at negative 78 degrees Celsius, we get the product we'd probably expect to get, where the bromine adds to the more substituted carbon and hydrogen adds to the less substituted carbon. But if we heat this reaction up just a little bit, 40 degrees Celsius, the major product here is this one where the double bond, we used to have double bonds on the first two carbons and the second two carbons. Now the double bond is on the middle two carbons. So what's going on? How does the double bond get there? Well, we have to look at the mechanism. And the mechanism is not really that much different from what we would expect, from what we remember. Alkene attacks hydrogen, kicks out bromine. From here, we get the more substituted carbocation. At low temperature, the bromine attacks here, we get the kinetic product. But at higher temperature, we can draw resonance here. And having the double bond here in the center is more stable. It's a more substituted alkene. And so the bromine will attack here, and we get the what might have been the unexpected product. And again, it's complete control over that, all based on your reaction temperature.